This lesson is an introduction to trig ratios. Trig ratios relate the sides of a right triangle to its angles. Each angle of a right triangle is equal to the ratio of specific sides of that triangle. Trig ratios are usually used to find side lengths and angle measurements. This unit focuses on sine, cosine, and tangent. The theta symbol is used to indicate which angle we are writing the trig ratio for. So the trig ratios for finding a missing side are sine, cosine, and tangent. Please learn the correct names: sine, cosine, and tangent. So the trig ratios for each of those are listed here. You can find the missing angles of a triangle by using inverse sine, inverse cosine, and inverse tangent. Again, those ratios are listed here. A saying that you can learn in order to help you remember the sine, cosine, tangent ratios is some old hippie caught another hippie tripping on acid. Acid's not an appropriate word for school, so you can say tripping on air. So learn the saying that works best for you. Sometimes these silly sayings do help you learn and remember the trig ratios. So some old hippie, the S stands for sine, old stands for opposite, hippie, hypotenuse. So that can help you remember the sine ratio. Caught another hippie, so cosine, adjacent, hypotenuse. Tripping on acid or air, whichever one you learn. T for tangent, on for opposite, and the A for adjacent. So let's write trig ratios for a right triangle. If sine is the ratio of opposite to hypotenuse, from our theta angle, so here it is labeled theta, the opposite side is this one C, and from our theta angle, the hypotenuse, which is always across from the 90 degrees. So sine of theta, be sure to include your theta symbol, is going to equal opposite, which is labeled as C, over hypotenuse, which is labeled as A. So that is the sine ratio for that theta angle. If you wanted to solve for that theta angle, you could use inverse sine. So the angle theta will be inverse sine of opposite over hypotenuse. So if we know those measurements, we could have calculated the angle measure. So let's set up the cosine ratio. It is the adjacent over hypotenuse. Of course, we've already labeled our hypotenuse. From the theta angle, the adjacent side attaches the theta angle to the 90-degree angle. So this side labeled B is adjacent. Adjacent. So side or cosine of theta is going to be adjacent, so that's labeled as B, over hypotenuse, which is labeled A. And so the same here for angle theta, we could use inverse cosine if we know these measurements of adjacent and hypotenuse. We could use those measurements to find the theta angle. And the tangent ratio. Tangent is opposite over adjacent. So again, from our theta angle, we have opposite labeled, that is C. So tangent of theta is C over our adjacent leg is B. And so to do inverse tangent, put your theta in there, angle theta is going to be inverse tangent of opposite, so that's C over adjacent, which is B again. So once again, if we knew those measurements of the triangle, we could find the angle. And we'll do that in later examples. Let's look at example 1. We're going to write the sine, cosine, and tangent ratios and its inverses for the theta angle. So here we have our theta angle. It may be best for you to go ahead and label your legs as opposite and adjacent, as well as the hypotenuse. Remember, your hypotenuse is always opposite of your 90 degrees. So many people start there with the hypotenuse. From the theta angle, imagine yourself standing at this angle. If you walk to the opposite side of a room that's this shape, you would walk to this wall labeled B. So this is not hypotenuse, but opposite. Going back to the theta angle, if you asked what is the adjacent wall to where you are standing, you would say it's this one here. Adjacent attaches the theta angle to the 90 degrees. So it's the leg of the triangle that attaches the theta angle to the 90 degrees. So now that we have those things labeled, we can write our ratios. So sine of theta, some old hippie, so sine, old hippie, we go opposite over hypotenuse. For cosine is cot another hippie, so again from our theta angle, cot another, so adjacent over hypotenuse. Some old hippie, caught another hippie, tripping on acid. So at our theta angle, tripping on is opposite, acid is our adjacent, so that's B over C. And of course the inverses of those, to find that theta angle, you can do inverse sine of that same ratio. The ratio of sine is opposite over hypotenuse. We've labeled those. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Use that saying, some old hippie caught another hippie, tripping on acid, to help you learn and set up those ratios correctly. Let's look at examples 2 and 3. We're going to write the sine, cosine, and tangent ratios and their inverses for the theta angle. So here we have our theta angle in example 2. Go ahead and label your triangle. Sometimes students prefer to start with the hypotenuse. Remember, the hypotenuse is opposite your 90 degree angle. Opposite the theta angle, we have this 4. And so the 3 is the adjacent. The adjacent attaches the theta angle to the 90 degrees. So once you have the things labeled, we can set up our ratios. So sine of theta. Some old hippie. So old would be opposite. Hippie would be hypotenuse. We'd say 4 over 5. Caught another hippie. So for cosine of theta, some old hippie is the first sine. Caught another hippie, so from our theta angle, another is adjacent, hippie, hypotenuse. So we say 3 over 5. And then tangent, tripping on acid. So tripping on is opposite, acid is the 3. So 4 over 3. And then we'd also write the inverses of those. I did not leave myself enough room to do such, so let's do a sticky note here. So our angle theta, we can do inverse. We can do inverse sine of 4/5. Or we could do, for our angle theta, we could do inverse cosine of 3/5. Or even for angle theta, we could do inverse tangent of 4/3. All of those inverse trig ratios would give us the angle theta. So let's look at example 3. Again, from our theta angle, here's our theta angle, 30 degrees. If it will help you to label it as theta, do so. So starting with sine, we have sine of 30. Since we know the measurement, let's use that in our angle. So sine of 30 is opposite over hypotenuse. So opposite of the 30 is this side that's 4. And the hypotenuse is always opposite of the 90 degrees. So some old hippie, opposite and hypotenuse, be 4/8. For cosine of 30, so caught another hippie, so from cosine, another is adjacent hippie, we go back to the hypotenuse, so 4√3/8. Tripping on acid for tangent. So tangent of 30, tripping is for the tangent, on acid, so opposite and adjacent. 4/4√3. So we can do our inverse ratios. Just in case I don't have enough room, let me bring our sticky back in. So our angle 30 degrees is going to be inverse sine of 4/8. Our angle 30 degrees is inverse cosine of 4√3/8. Or we could also do angle 30 degrees is inverse tangent of the 4/4√3. So we can check number 3 in our calculator. Sine of 30, we can punch that in the calculator and that should equal 4/8. In addition to, we should get 30 degrees when we do our inverse sine. So let's do this now in our calculator. Before doing so, this is very, very, very important. The calculator can be used to check your ratios, but the calculator must be set in the correct mode. In order to put your calculator in the correct mode, you're going to press the mode key. It's there at the very top. Of course, have it turned on. So there at the very top, hit mode. You're going to arrow down to the line where it says radian and degrees. So arrow down to the radian degrees, and you're going to highlight degrees. So arrow over so you can highlight degrees and press enter when you're on that. And notice that it has changed to that degree mode. You can press second quit or second mode to get out of that menu. If you want to make sure that it stayed in degrees, just hit mode again, and we see that degrees is highlighted, so it is in the correct mode. So we can check our answers from number 3 with our calculators. So if you hit sine of 30 and close that parentheses and press enter, notice we get 0.5, and 4 divided by 8 is 0.5. We can check cosine of 30 as well as 4, the square root of 3. Because this is in a fraction form and our calculator does do order of operation, it may be best to tell the calculator that you want it in a fraction. So if you press alpha y equals, alpha is the green button, y equals that first row button, you get that fraction menu. So that first option allows you to put it in as a fraction. And notice again, those do match. Cosine of 30 and that fraction are the same. Let's check our tangent of 30. and the fraction. So we could start with just saying alpha y equals first instead of typing in the numerator. So now our fraction has 4 over 4, the square root of 3. And again, those do match. In order to get the inverse trig ratios, notice in blue above the sine, cosine, tangent buttons are the inverse. So now if we do second inverse sine of 4 over 8, it gives us 30 degrees. The same will happen for our inverse cosine. Do your alpha y equals to put in your fraction. So we've got our inverse cosine, and once again we got 30 degrees. And then finally we could check our tangent, inverse tangent. Alpha y equals. And when we check this one, we'll find that is also 30 degrees. So this is always helpful to check, but it's very rare that you'll have your angle and the ratio. Sine, cosine, and tangent is used to solve for one of those pieces, but if you are given each of those pieces, it is nice to check and see that they are equal. But later we'll use these to actually solve. So maybe this 4 will be missing and you'll have to solve for that value. Or the 30 will be missing and you'll have to solve for that value. Of course, that's when we'll use the inverses. Let's go on to example 4 now. This will kind of start getting your mind set up for solving. We will need to determine which trig ratio to use. So example number 4. Notice where the theta angle is here. We've got it labeled as 32 degrees. So if it helps you to put a little theta symbol in there, feel free to do that. From that theta angle, we know the opposite and we know the adjacent. We don't know the hypotenuse, so there's no need in labeling that. We only know the opposite and we only know the adjacent. So opposite adjacent. So if you think back to your sine, cosine, and tangent ratios, some old hippie, that would have to have the hypotenuse, caught another hippie, again would need the hypotenuse, tripping on acid. So that is tangent. Tangent of 32 is going to equal opposite, which is 5 over 8. Because we know all of those values, we could check those in the calculator to see that we have set that up correctly. But in future lessons, we would just be solving for one of those, so we wouldn't have this as an option to check. But now's the time to check when you're just learning the ratios. Let's write our inverse of that angle. So 32 degrees should be our inverse tangent of, again, opposite over adjacent for tangent ratio, so 5 over 8. So if we check that in the calculator, inverse tangent, typed in the 5 over 8, it should spit out and give us 32 degrees. Let's look at our next example, number 5. Here, looking at our theta angle, it's labeled as 60 degrees. We do not know the opposite, so there's no reason to label this as opposite because we don't know it. We do know, though, the adjacent. Remember, the adjacent attaches the angle to the 90 degrees, and we also know the hypotenuse. So across from or opposite of the 90 degrees is the hypotenuse. So some old hippie, it would not be sine because that would need the opposite, caught another hippie, that is what we have. Adjacent and hypotenuse is what that another hippie stands for. So here we can set up cosine, because that's adjacent and hypotenuse. Cosine of 60 equals our 3 over 6. So again, you can check that in the calculator, punching in cosine 60 and then 3 over 6, and see that those both equal 0.5. Using our inverse of that angle, we would just say 60 degrees equals our inverse cosine of 3/6. Again, we can check that in the calculator, doing inverse cosine of 3/6 and get out that 60 degrees. Let's look at our final one here. We've got our theta angle at 56 degrees. We know the opposite side, and we know the hypotenuse. So some old hippie, that's what we've got, an opposite and hypotenuse. So that right away is sine. Some old hippie. Sine of 56 equals 5/6. And then we can do the inverse of that. So 56 degrees equals the inverse of 5/6. Let's check this last one in our calculator to see it one more time. So if we type in sine of 56 and then 5 divided by 6, although those decimals are not exact, they're very close. There must have been some rounding within this problem, but that is close enough. I'm going to call it, especially when you round it up to the nearest hundredths place, those will be the same. So sine of 56 and 5/6, I do agree that those are the same. And then inverse sine of 5/6. Here we see 56 degrees. Again, it did round. If we round it to the nearest whole degree, that's why it's not quite coming out the same, because there is some rounding involved. And I am fine with that. It is close enough to say it is correct. Let's look at one other theorem that comes up in our work. Here we have our trig ratios of complementary angles. If you'll remember, complementary angles mean that they add to equal 90 degrees. Because we're dealing with right triangles, the two acute angles in the right triangles are complementary. So here's a fun little example to hopefully help you learn this. Because this is a right triangle, the star angle and the smiley face angle are going to be complementary angles, meaning that they add together and equaling 90 degrees. So let's imagine that we're wanting to do the sine of the star. So here we're at the star angle. I'm not going to label this triangle as opposite, adjacent, and hypotenuse. We can name the hypotenuse, it's the frog, because it would never change. But from the star angle, you'll have an opposite and adjacent. But when we switch to the smiley face angle, those things would change. So I'm not going to label them. We're just going to look and visualize those sides. So from the star angle, if we're talking about sine, that's some old hippie. That's opposite and hypotenuse. So opposite the star is the fish. And we already talked about this frog as hypotenuse. So sine of the star is fish over frog. Okay? But now we want to switch to the smiley face angle, and we want to talk about cosine. So caught another hippie. From the smiley face angle, we want to find cosine. Caught another hippie. So another stands for our adjacent, that's the fish. Hippie, again, is that hypotenuse. So again, we see the fish over frog. So sine of one angle equals cosine of the other angle when those angles are complementary in our right triangle, meaning they are the two acute angles of the right triangle. So that just means that they are equal. So for our last example here, number 7, if we know cosine of A is 0.35, we want to find the sine of B. Well, we just talked about the cosine of one of the angles, so cosine of angle A is going to equal, the cosine of one angle is going to equal the sine of the other angle. So if cosine of A is 0.35, then that means our answer for sine of B is going to be 0.35.